All right, it's now 6:30, so I'd like to welcome everybody here for the first ever ANZAAS Zoom Science Talk. This talk is very much an experiment. It's the first one that ANZAAS has held, and ANZAAS is now 133 years old. For those who aren't aware, ANZAAS is the Australian and New Zealand Association for the Advancement of Science. We're Australia's oldest nationwide science organisation, and we're also one of the few science organisations that's primary focus isn't for the elites like the academies. It isn't for the focused on education. It's focused on all of the above. Anybody who's interested in all things scientific is welcome at ANZAAS. Now, I'd also like to acknowledge the support that ANZAAS has received from CSL to hold the ANZAAS Melbourne Science Talk series, which are normally held in GTAC in Parkville. But with this COVID Zoom move, then hopefully these talks will have an even wider audience. I'd also like to acknowledge the traditional owners of the land, at least the ones on whose land I am. They're the Wurundjeri people of the Kulin Nation, and pay my respects to their elders, past, present, and emerging. Now, during this talk, I'll invite people to ask questions using the chat function of Zoom, and then as those questions appear, I'll pass them on to Professor Brooks. Now, our speaker tonight is Professor Geoffrey Brooks. He completed his PhD in 1994 and then worked at the University of Wollongong, but he's also worked at McMaster University in Canada, at the CSIRO, and then at Swinburne that he joined in 2006. He's been the Associate Dean of Research, Head of Mathematics and Pro Vice Chancellor for future manufacturing. He currently works in the field of high temperature materials processing, and he is working with physicists on dark matter detection research. But today he's going to be talking about green steel. Can we decarburize steel production? So without any further ado, I'll hand over the controls to Geoff and ask him to give his presentation that I'm looking forward to very, very much.
All right then, well, I'm excited as well to be here. When I was a student and also a young engineer, I went to several ANZAAS talks and I enjoyed them, so it's nice to be a speaker at one. I hope everybody can see my slides. Are they clear, David? You can see them?
They're very clear, yep.
Yeah, thank you. What I want to say straight away is there is a danger. I'll be talking about something I love a lot and care a lot about. So if I start going on too much, please, David, put a wink at me and I'll try and stop going. But I think I'm talking about a very important topic, a topic that is at the moment, I would describe as one of the hottest topics in engineering at the moment, which is the whole issue of how do we decarburize our industries. And right at the heart of that is one of the major industries, the steel industry. What I'm going to do is I'm going to explain to you some of the basics so that you can understand why there are limitations. I do see some very naive things said in the media about this topic, and I want to try and explain some basics. And then I'm going to talk about some of the very recent developments in Europe. And in fact, I've got some data provided to me from a German steelmaker from a week ago. So really hot off the press. and we can see some of the things that are going on and talk about the repercussions for Australia and what we could possibly do. So, and it is important to Australia, as I will explain. All right, so can we decarburize steel? That's the essence of this talk. First of all, we need to appreciate the big picture. So steel making is about 8%, produces about 8% of all the world's CO2. Some people say 9%, some people say 6%. Let's settle on 8 for a number. It's a very large industry. It's a very important industry. It employs millions of people. I think everybody in the room would understand that steel is a very important commodity. And Australia plays a very important role in that whole world industry. And this industry is not surprisingly under pressure to decarburize because it's a major industry. And we know that particularly in Western economies, but not just Western countries, we're also seeing it more increasingly in Eastern countries as well, this shift towards a circular economy, the notion that we shouldn't have to be, we should be able to make our way of living largely carbon neutral, or at least a very neutral level of carbon. And underneath that kind of desire is two rather big issues which relate directly to this topic. And the first one is, how do we link renewables to heavy industry? It's pretty self-evident we can link renewables to, you know, household supply. We can find all sorts of clever ways of saving energy at a sort of local level. But what about these big industries, these really huge industries like steel and cement and fertilizer industry, etc.? How do we link them to renewables? That's not so clear. And then recently, people have been proposing that one of the ways we can do that is by using hydrogen. And people are saying hydrogen's the answer. And in fact, it's become a sort of, it is a bit of a hyped up idea at the moment. I think it's an exciting idea, but you do hear a lot about it. And I think we need to pull it apart a little bit and have a look at how it works. And I think by talking about the steel industry, you'll see some of the generic issues around hydrogen. You'll see some of the things that we have to think about when we say we want to move to hydrogen. So let's talk through some of those. So the first thing is, let's just get a picture of metals. So there's a little bit of metallurgy 101. And one thing to realize straight away is that steel is huge, absolutely enormous industry. And what we see here are some of the principal ores in the world and how many tons a year are roughly made of these metals. And you'll notice that steel is over 1,800 million tons a year. I want you to try and imagine what that means. And aluminium is 63.7. That's the second metal. So steel is an enormous industry. And it's also growing. It's doubled in the last 20 years. So steel's not flattening. Steel is not on some sort of plateau. It's still growing. It's plateaued in a lot of Western countries, and there's good reasons why, which we'll talk about. But on a world level, it's still continuing to grow. And the only thing that's really comparable to steel that I can think of is cement. And cement is, you know, I put it there, it's sort of around, it's a bit that double the size. And when you look at some other materials that you hear a lot about, like plastics and fiber composites, you realize just how enormous steel is. To give you some sense of it, if you've ever been to Wollongong, the plant at Wollongong was designed for 5 million tons, all right, to make 5 million tons a year. So basically the world is 1,800 divided by 5 Wollongongs in the world. And I mean all Wollongong, I mean the harbour, I mean the schools, I mean the railway, I mean all the infrastructure as well. So we're talking about some enormous industry. And that raises a very interesting question, because in that list of metals I put there, I mentioned titanium, magnesium, aluminium. They're very impressive metals with very impressive properties. Some of them are titanium and aluminium, a lot lighter than steel. So why is steel so huge? What's going on? Well, it would take me a while to go through all the reasons, but one of the most important reasons is because you need a lot less energy to make steel. So what we have here is some calculations done by my old PhD supervisor, actually. And he did these calculations at CSIRO, and he looked in Australian conditions at how much energy is required to make titanium, magnesium, aluminium, stainless steel, and steel. And on one side, he's got the energy, and on the other side, he's got the global warming potential, so how much CO2 is associated with that production. And of course, you expect those two things to be quite related, and they are. And you can see that steel absolutely is incredibly less energy intensive than titanium, magnesium, and aluminium. And this is why steel is so popular. It's got good properties. It's not as light as some of those metals, but it's got excellent properties, and you don't need that much energy to make it. All right. So the thing about steel is it's already a relatively high efficient industry, but of course, a tiny difference in steel is a big difference in the world. You know, so it's one of the things that's motivated me to work in steel. I haven't worked much on titanium, but I've worked a lot on aluminium and magnesium, and a bit on stainless steel. But one of the motivators of me working on steel is the pure importance of it to humanity, the pure scale of what it means to improve something in steel. So I hope that gives you some sense of the scale of what we're talking about. And Australia is a major player in this game because we are a relatively minor steel producer, but we are a very large iron ore exporter. We're one of the great iron ore exporters of the world, probably the greatest. Maybe Brazil would challenge us. And when you look at iron ores, they come in basically two major sources, hematite and magnetite. And there are other ores, there's goethites and siderites. And these ores, if they were pure, would be above 70%. But in reality, they're lower than that because of all the impurities. And the impurities are very, very important to what we're discussing tonight. As you'll see, they're not trivial issues, and they're not trivial to Australia. And basically, you'd say a high-grade ore is 65 and above, and a low-grade ore is sort of, anything below 60 sort of type thing. It becomes a lower-grade ore. And the impurities, which are normally silica and alumina, they add a lot of issues to the steelmaking process. And the one thing that really adds a lot of problems to the steelmaking process is phosphorus. And I'd have to give a very boring half-hour lecture on thermodynamics to fully explain to you why phosphorus is such a nuisance in steel. But the basic reason is because it behaves chemically very similar to iron. It has a very similar chemical behavior to iron. Therefore, it's extremely difficult to get out of iron because you're trying to remove something like iron from iron. All right, so that's basically the problem. Whenever I teach the thermodynamics of it, I use football analogies about taking Collingwood supporters out of a team of Carlton players, etc., to try and explain what the issues are with phosphorus. But basically, they behave quite similar to each other. And as I mentioned, we have a giant iron ore industry. I think everybody in the room would be aware of that. And this, the industrial revolution of China, which must be probably the greatest it is the greatest industrial revolution of all time. It's fueled an incredible growth in our iron ore industry. And I think everybody be aware of the incredible money associated with iron ore over the last 20 years. And so this has a great deal of bearing on the wealth of Australia. And a really big issue that we're going to talk about tonight is if we move to a hydrogen economy, what does that mean to our iron ore industry? And that is a very interesting question that's actually keeping a few people awake at night. So we'll talk a bit more about that. This is some compositions of Australian ores. They're slightly out of date, but they're probably not that far away from what is being dug up at the moment. They're probably a bit poorer in quality just at the moment. And you'll see that Australian ores, you see a lot of them are around about the 60%. And that means they've got quite a bit of impurities in them. So that's not a minor issue because we're the big iron ore seller of the world. So every time you see those impurities go up, it becomes, less of a saleable product. And so one of the big issues facing the Australian steel industry is they dig away, the iron ore industry, sorry, as they dig away more and more ore, they get to lower grade ores, and then we've got to find ways to try and improve the quality of the ore in a financial way that will allow us to keep selling these ores. So this great iron ore boom, we shouldn't just assume it's going to keep on going. There are major technical issues there. And I've done personally a lot on trying to upgrade magnetite ores. I won't talk about that tonight. That's a whole separate topic in itself. But these are big national issues, and there's a lot of serious people working on it. This gives you an idea of how ore grade is changing with time. So we see here some historical numbers. This has been put together by my friends at Monash and RMIT, did a nice study on this. And they show here the way in which ore quality is changing with time. And you'll see that Brazilian and Australian ores are at the top there, sort of around about the 60, 61, 62%. And we see Chinese ores aren't very good, well, fortunately for us, because they want to buy our ores. And you can see there's a general trend down, as I described. And basically what's happening is we're digging up all the good ores, and we're less with the less good ores. We're less with the ores that aren't as impressive. So this is going to be a big challenge, not just for Australia, but for humanity, and about how we're going to deal with that, because there are all sorts of energy repercussions to the degrading of these ores. And then, of course, the products. And well, I suppose you'd have to be you'd be quite an ignorant person not to realize the importance of steel. And here's the major products that come from steel. Infrastructure is enormously important in the developing world. And on the right-hand side, we have, domestic appliances, automotive, and these become more important as you become richer. So basically, when China is progressing across that graph, right? So 20 years ago, they were all about building things and buildings and bridges and railways, et cetera, et cetera. And as they get richer, they'll become like us, and they'll start buying fancy domestic, well, they already are, the fancy domestic appliances and imported Swedish kitchens, and and they'll push across that graph, across that line of products. And basically, it's more complicated than this because there are literally thousands of steel alloys. But basically, as you go to the right of this diagram, it's more difficult to make, it becomes more tricky, it becomes a more difficult thing to produce. So there's a lot of knowledge in being able to make all those different products from steel. But that gives you a sense of the breakdown of steel, where steel is used in the world. Now we get to the topic, which is, well, all right, that's great. What's this? This uses a lot of carbon, and in fact, indeed, the world's steel industry is, as we mentioned, 8% of the world's carbon dioxide, depending who you ask. And basically, the Paris Agreement says we need to get that down to 400 to 600. So that's a very large change, and by 2050. And when you look at trying to work out how steel production will change over the next 35 years, it's almost certainly going to grow, and it may even grow more than what they're predicting in this particular diagram, but they're having a guess, an educated guess. And then we've also got to that means that we've got to find not only ways to get rid of the carbon from the existing process, but the future steel production. And you can see on the right-hand diagram, we're showing just what an incredibly large change we need to make to the intensity, how much carbon dioxide we produce for each ton. We're talking about 90%. We're talking about, so we're not talking about an incremental improvement here. We're talking about a revolution, right? So this is not a mild change, and this is what's keeping steel executives and iron ore executives and professors who work in this area awake at night. How are we going to do that? How are we going to make that happen? So that's an exciting but also interesting challenge. Now, I have an unfortunately busy but important diagram, so I'm probably going to spend the most time on this slide because it's important to understand. Basically, there are essentially three major ways of making steel in the world. And the biggest way is we start off with ore, and we get coal, and we turn it into coke, and we take it to a blast furnace. That's the one at the bottom there, right? We put it through a blast furnace, and we make iron. And that iron then goes off to a steelmaking process, the basic oxygen steelmaking process, where you make steel. And then the steel is refined, and then it's cast. And it's generally either cast into what they call flat products or long products. And flat products end up in your refrigerator doors, in your cars, and your long products are reinforcing bar and beams and such things, right? And the other major way that we make steel is, the second major way, is we get scrap steel. We get the steel scrap. This is what they do in Sydney and Melbourne at the Sydney Steel Mill and the Lavender Mill, where my friends work. And we get the steel, scrap steel, we put it in an electric arc furnace, and we melt it, and we refine it through a ladle, and then we cast it into these different shapes. All right? So that's the second major way, running in the middle there. And the third major...
How much energy is needed for recycling versus new steel?
Oh, David, about half, but hang on your horses. I'm going to that in quite some detail. Yeah, yeah. I'll give you information, about half, roughly speaking. And then the third way is that, which is becoming, looks like it may become extremely important, it's at the moment the third way, is we get iron ore, and we get mainly natural gas, and put it through a shaft furnace, which they call a DRI process, direct reduction. And this DRI product goes into an electric furnace, we refine it, and we make steel. And that's probably about 10% of the world's steel is made that way, roughly speaking. All right? So these are the three dominant ways. Now, I'm sorry, I can imagine that's a little bit confusing. I think it'll become a bit clearer, so we might go back to this diagram, but just to get the general gist of it. The blast furnace is the dominant way of making iron, and the blast furnace has been around for hundreds of years. We've put tremendous development into the blast furnace, and it's essentially a solid gas reactor. You've got gas going up through this, blasting through these tuyeres, and it goes up through the middle through the furnace, and it reacts with the iron oxide. It's burning, it's basically converting carbon into carbon monoxide down the bottom here, and it goes up through this shaft, and you go through this sequence of reactions. So the solids going the other way, the solids falling down, and as the solid falls down, it goes from hematite to magnetite to FeO, the FeO being reduced to iron. And then molten iron forms at the bottom. So solids this way, hot gases going that way, all right? So it's a solid gas reactor. And it's very old, but it's also very impressive. It has very high energy efficiency, so like 85%. So for example, power stations are typically 35 to 40%. So it's a very efficient reactor, and there's been a lot of investment. Actually, I'm happy to report to you that Australia's been very clever in blast furnace technology. Professor Ibing Yu at Monash and Paul Zuli at University of Wollongong. They've done a lot of work in this area to improve the blast furnace, working with companies. Anyway, this process relies on coal and coke, and the coal is turned into coke because these are very tall vessels, and the coke provides the physical strength and structure to be able to hold all this ore up. So you can't just put any kind of coal in there. You've got to put a certain sort of coal that can be converted into coke. And that is very important to Australia as well, because we're one of the world's great coke producers. So this is how about 70% of the world's steel is made via this process. And there are a lot of details, as you can imagine, but that's the broad picture. One thing that's important to appreciate, because it's going to become quite important when we talk about these new processes, is that as you add carbon to steel, iron, the melting temperature decreases. So you'll see here that pure iron's about 1534 degrees Celsius. And as you add carbon down this line here, its melting point lowers down to about 1180, or there, 1147, written on the diagram for me. So that is very important, because that means the blast furnace can melt this materials fairly easily at the bottom of the furnace and produce this as iron product that we tap out of the furnace. Just a little important fact to appreciate, you'll see. Now, when you look at this process, the blast furnace and the oxygen steelmaking process, this is the big one in the world that makes most of the world's steel. The blast furnace dominates the CO2. So you can see when you look at the total CO2 coming from the process, it's the blast furnace that is making most of the CO2. Now, there is other ones associated with the other parts of the process, coking, for example, sintering, but it is the blast furnace that dominates. So this is where all the attention is at. If we want to decarburize the steel industry, first step is do something about the blast furnace. Stop putting so much coal into the blast furnace, right? How could we do that? So this diagram shows that quite clearly. Now, I've just been talking about the blast furnace, and I think because that previous diagram is very busy, I think I just broke it down into a smaller step so everybody gets what's going on. In the blast furnace, we get ore and we turn it into sinter or pellets, and we put it into a blast furnace. We then get coal and we turn it into coke. We put it into the furnace, and out the bottom becomes a liquid product, which is called pig iron. And it has about 3% carbon. All right. On the other side, the other way of making iron that people use is they get DRI, they get iron ore, they put it into a pellet, pelletize it somehow, and then they react it with natural gas, and they form a solid product, It's not liquid, it's solid. You can transport it, you can ship it, you can put it on a ship. But because it's never been liquid, all the gang materials are still in it. It has all the gang, all those silicas and aluminas that we're talking about before are still in it because it's a solid product. So DRI is essentially a solid product with lots of gang, and pig iron is a liquid product with no gang. Right? So that's something to appreciate about the different forms of iron that we're going to talk about now.
So gang, what does that stand for? Is that an acronym?
Yeah, it means that the materials that you don't want.
Right,
Silica,
so it's like
alumina,
slag, only it's
like slag.
Yeah,
it's the gangs before it becomes liquid. Yeah, so yeah, it's a slag. It's a residue you don't want. It's there, right? So now there are quite a few DRI processes being developed over the world, but the biggest ones are Midrex and HYL, and you can see here that since 1990 to just a couple of years ago, that's gone up to 80 million tons. So once upon a time, DRI was a very minor way of making iron. Now it's quite a significant way of making iron. It's quite well established. Some people are saying that graph, which we're about to explain, needs to go up really, really, really steep, and we need to start using hydrogen in that process. That's essentially what people are putting forward. The DRI process, I won't go into the details of it, but something you need to know about it that's very, very important is that it currently operates sometimes up to 90% hydrogen. I wish to repeat that. Currently, using natural gas, they use up to 90% hydrogen. So in other words, we already make a significant proportion of iron using a very high level of hydrogen and not generating CO2 via this process. So you can imagine why people are excited that this could be the answer to decarburising the steel industry, because we already get pretty close to that. And this process is very well established, and you have plants say up to 2.5 million tonnes a year. And if you believe what people are saying at the moment, then when you drive through Wollongong or you drive through Whyalla, in a few years from now, you won't see a blast furnace, you'll see one of these, right? Or something like this, right? So this is the kind of argument we're hearing at the moment. Now, here's the graph that David was asking about. This is an important graph, all right? So what we have here is kilograms per CO2 per steel, and this is the standard route, the blast furnace and the BOF. And then I won't go through all these other ones here, but here's an important one, the one you asked about, which is scrap in an EAF. And you can see that the scrap in EAF is a lot lower number. Please notice if you go down to scrap with a renewable energy source for the EAF, it goes down to a very small number. And if you go to this one, which is basically a hydrogen DRI process they're making in Sweden, it's a tiny number. So what I'm about to say in a complicated way is that these two are the answer at the right-hand side, right? These are two things that we could do that would dramatically lower the carbon footprint of steel. And we know how to do them, which is a little bit exciting, all right? So in other words, the answer is there. Well, the answers are there. But as you'll see, there's a few complications that are very important to understand. So why don't we just stop digging up iron ore? Why don't we just use scrap? That's a question I'm sure some of you are asking, and go fully circular. Well, when you look at the supply of scrap in the world, it's not as large as the steel produced, all right? But it's a good proportion of it. So there is some arguments of saying that we need to just be smarter with the way we make products. We need to start thinking about not using as much steel and trying to live on the scrap. Actually, one country that is getting relatively close to that is the USA. So even though we sometimes say the USA is not very environmentally sensitive, and particularly one side of politics there, actually they have a very, very large level of recycling going on. And that already, as you can see from the previous diagram, substantially lowers your carbon footprint. So the Americans are a fair way down that path. But if you go to China, they don't make much. Sorry.
What's obsolete scrap?
Things that obsolete equipment.
All right, so it can still be used and put into the
into the process. Yeah, it's not obsolete. It's not obsolete for recycling. It's obsolete for use. Yeah. So here's my decarburization strategy number one. So I'm going to present two major strategies. Right. First strategy: let's move to scrap-fed EAFs, and more. Let's actually use renewable energy. Let's connect the renewable energy to the EAFs, and that would straight away dramatically lower the carbon footprint of steel production. That sounds easy, doesn't it? Well, it's not easy because there's some complicated metallurgical issues. The first complicated metallurgical issue is that there is a lot of residual elements, contaminants in scrap. And when you're trying to make high quality steel, it's actually non-trivial to be able to get rid of those residuals, very non-trivial, in fact, sometimes impossible, I'd say. And one of the worst ones is copper and tin. So if any of you ever throw some copper or tin into a pile of steel scrap, you are a great enemy to steelmakers. They would probably want to know your address and come and send a nasty message to you. It's almost impossible to get those elements out of steel. And so there are metallurgical issues. There are also social political issues. We are going through enormous pain about the future of Whyalla. Can you imagine if we said, let's close all the blast furnaces in China and Europe and Japan? And we're talking about disrupting hundreds of cities. We're talking about the disruption of an enormous amount of capital and human investment. So the social and political repercussions of such a move would be extraordinary. But in principle, this is the simplest way to dramatically lower the carbon footprint of steel, is by moving to scrap with renewable energy supplying the electricity. All right.
Do they still use tin in tin cans, tin coating of steel?
Yes.
And is that a problem?
Yes.
Are there good alternatives? I guess if there were, they would use them.
Yeah, but they try to avoid that. They try to avoid that being put into the process. Yeah.
And if
So,
you can't recycle tin cans, then it makes it.
not very readily. Actually, a good question. Off the top of my head, I don't know what they do with tin cans. It's a very good question. I have to think about it, Doug. So what's this mean for Australia? Because I said that's what it means for the world. What does it mean for Australia? Well, for Australia, we have 2 large scrap melting shops, one in Sydney, one in Melbourne, and they all are running off electricity from coal-powered stations, and they also use quite a bit of natural gas as a help put energy into the system. We also export scrap to Asia, quite a lot of scrap. And one of the reasons why we export scrap is because we haven't built enough EAFs. We really should have an EAF in Brisbane, in my opinion, because that is a large population base. Basically, an electric arc furnace fed on scrap bases itself on the population around it, right? So if you've got enough people who are buying fridges and cars and all the rest of it, then you can justify having an electric arc furnace and you can make a good business from it. So I think the future challenge for Australian first decarburisation strategy, the easiest one, is to bring renewable energy to our electric arc furnaces. So we're going to come up with a plan to bring renewable energy to our large electric furnaces. That is a quite doable thing. We have the technology, and I think we have the know-how. So that's a simple strategy. And build more EAFs so that we don't have to export our scrap, which is, I think, sort of a mind-bogglingly unintelligent thing to do from a national perspective. And then the bigger challenge, all right, if we do that and we start trying to live off our own scrap, right, then we have to start making higher grades of steel. Because at the moment, we're making the relatively simple grades with our recycled steel. But if we want to start being a circular economy, then we're going to have to start making all the grades of steel. So we're going to have to get clever, and we're going to have to become quite smart at sorting our scrap. Now, I can report some nice news about that. I get supported by all the steel companies, of course. I work a lot in steel. And I did a very nice project with InfraBuild, where we tried to assess the feasibility of monitoring the elements coming into the scrap and then using that to improve the process. And they gave us a lot of data, and we also did a lot of interesting work with a Brazilian university. And we wrote the paper. When I wrote it, when you write most papers in this area, you don't always get much reaction. But I published it, and I got so many queries from around the world. And then last year, the Institute of Materials and Metals in London-based organisation awarded this the best paper in steelmaking in the world last year. So it's a nice story. But we're going to have to do a lot more of this, right? If we're going to move towards a circular economy, we're going to have to get clever and clever at how we sort our steel, how we characterize our scrap, and then how do we control the process. So we're going to have to do a lot more of this kind of thing and implement some technologies. But I believe it's doable, and I think we can do it. Obviously, I believe we can do it. The next strategy, so I'm now getting to the next big strategy. Right. As I've been implying, move to hydrogen-based iron making. Right, that's the next strategy. Right, let's decarburize by using hydrogen. We know that hydrogen can be worked. So the questions that come from that is it affordable? Can we make enough hydrogen to do this? Is that possible? Right, that's a big question. Second question: do we use green or blue hydrogen, which I will explain in a minute? And can we adapt the existing technologies, or do we have to build something different? It's another big question. Remember, the world steel industry, particularly China, has invested literally billions and billions of dollars into their furnaces. So you don't casually just bulldoze them down, do you? Can we adapt the technology to this hydrogen fuel? That's the big question. And what will be the impact on the steelmaking? This last point is not thought about very much in the popular press. When you read people talking about this, there are serious impacts, which I'm going to explain to you. So what would a hydrogen economy look like? Well, we would have renewable energy, electricity, wind power, pumped solar, pumped hydro, etc. And we would use electrolysis, which is a known technology, to make hydrogen. And that hydrogen would be stored, and then it would be used in transport, or used for electricity generation, or used directly into our process. And we'd use fuel cell technology to fuel transport, et cetera, et cetera. It all sounds wonderful. If you look into the details, and I'm not an expert in hydrogen storage and such things, but I know a bit about it. It's quite complicated. It's quite a complicated thing. There's a lot of issues about materials. There's a lot of issues about safety. There's a lot of issues about just utilization of the hydrogen. They're not trivial. Doesn't mean they're not solvable either, but they're non-trivial. There's certainly significant issues. And there are very significant social issues, right? So if you say, I want to go and build a hydrogen storage facility next to your house, one can imagine, this is not a simple thing. There's many issues there. And now we get to this business about blue or green. So the classification that people are using in the world to stop explaining it over and over again is blue hydrogen is using existing technology that's well established, either by steam methane reforming or gas or coal gasification to make the hydrogen. And then the CO2 that's generated from that process is then goes through a carbon capture technology. They call that blue hydrogen. And that is, each one of those steps is relatively well known. All right. In other words, we know how to do it. There is controversy about the carbon capture one. All right. So there is some political, economic issues around that, but we know how to do it. There are ways of doing it. In the case of green hydrogen, we also know all the steps as well, but at a lower scale. So in the green hydrogen, you use the electrolysis of water fueled by renewables to make oxygen and hydrogen, and you feed the hydrogen to the system. And we call that green hydrogen, right? Just to explain the lingo, the language. And as I mentioned to you, the water electrolysis is relatively well established, but not at large scale. And there are two major technologies. One is an alkaline system that has a membrane to separate the two sides of the electrolysis reaction. And there's another one which is called the proton exchange membrane, which has a solid barrier between the cathode and anode. And it was developed in reaction to some of the perceived weaknesses of the alkyne technology, in particular current density. So any of you there who've studied Faraday's laws at some stage will know that current density is very important in the economics of electrolysis, right? If you can make a lot of hydrogen for your square meters, essentially. So these technologies are quite well established and they're well known, but they're not at large scale, all right? So they're relatively small scale. And to give you some sense of it, Air Liquide is one of the major companies of the world that is actually working with the steel industry. They're a big gas company, but they work very closely with the steel industry. And they are heavily involved investing in hydrogen technology. And this is from a presentation from last year. And their biggest plant using green hydrogen is 20 megawatts. Well, that's an awful lot of power to you and me, but it's not an awful lot of power compared to a steel plant, all right? So to give you some idea, here is a Midrex system, which they're putting forward to produce using hydrogen. And they did some calculations on a 2 million ton plant, and they came up with 650 megawatt hydrogen plant is required for this plant. I'll just repeat what I said. This commercial plant is 20 megawatts, right? So we're talking about some very, very serious engineering issues. So at the moment, there are plans all around the world, particularly in Europe, to build very large green hydrogen plants. And everybody in the steel industry is watching with great interest about how that will work, because there are issues about stable operation, there are issues about safety, there are capital cost issues, particularly capital cost issues. But optimistic people think that they can scale up and improve the economics, and other people say, well, I'm not sure about that. So this is a very big question at the moment, and the world is watching. But just to give you some sense, state of the art, 20 megawatts, what's required? Over 600, all right? So that's a big jump. Now, there's been a lot of people doing calculations about how much this green hydrogen route to steel will cost. And I'm not going to get into the details of it. I do know some of the details, but it's a very unfortunate debate because it tends to be very specific to the location, the particular technology, and the details of what you're discussing, right? So I just attended a conference, or virtually, a conference in America where lots of people were talking about it. And to give you some sense of it, an expert, highly respected expert, Sarah Hornby, who's a big electric furnace expert in North America, she was estimating that hydrogen will add 55% of the cost of steel in America. Another speaker was looking at some calculations from the Institute of Energy, and he came up with a 43% increase value, right? I've seen other papers that say more like 20%, etc. This graph here illustrates some of the cost points. So what we see here is the cost of hydrogen going down from 3 to 2 to 1. There are quite a few people that believe that we can get it down to 2, in the near future, or 5, 10 years sort of period of time. There are also people who are pessimistic who think we're going to struggle to do that. I don't read many people who think that we can get it below 1. All right, I haven't read many people who think that. But even at 1, we're adding 20% to the cost of the steel. 20%. Right? That is not a trivial issue, because remember, whoever does that has to compete in the world. So you'll notice that the European Union last week said, if you start selling some of your steel using carbon into our market, when we decarburize, we're going to tariff you. And I think they said 2036. And that's the reason why. Even the most optimistic person in this area doesn't think that, the $1 is a quite optimistic number, all right? So there's a lot of debate about whether we can take it from 3 to 2 in terms of cost. And as I said, it depends a lot on location and the details, etc. But, taking it below 1 would be a major challenge, all right? And this graph is also showing, though, that steel is a very good candidate, because when you compare it to ammonia production, steel looks rather good. So steel is seen as a very good candidate for this decarburization. So is hydrogen the answer for steel? Well, there's issues around handling and safety. This whole issue about carbon capture, that's a very controversial technology, because it involves pumping hydrogen often, well, it doesn't always, but involves often pumping hydrogen down into large underground storage places, like, for example, old oil fields and such things. And, how acceptable is that politically and socially, I think is not trivial. There are also debates about the cost. But what must be said is that there's quite a large knowledge about carbon capture technology. So we shouldn't sneeze at it. In other words, there is a lot of knowledge there, and maybe it's part of the answer. Some people say, for example, our current federal government does believe that some sort of carbon capture combined with a move towards renewables is what we need to do. And I can see the arguments both ways if I try and put the politics aside. So anyway, at the moment, we can say with some accuracy, the green routes for making hydrogen are at quite low scale compared to what is required for the steel industry. And we could also say current green hydrogen is relatively expensive. So there's a lot of room for innovation in this space. And I know there's good people in Australia working on that. And if I've insulted anybody in the room who's working on it, I'm sorry, please, you correct me. If you think it can go below $1, for example, I'd be quite interested to hear about it. So what are the major options? Well, we can stick it into the blast furnace, as we said. You can put it into a DRI process, which has already been largely shown to be correct. And you could also put it into a fluidized bed. And this has actually been done at commercial scale. We've already done it. It's already a done deal. We've already actually demonstrated this. And another thing, which is the fourth one, is perhaps we really need to rethink the whole steel process in light of this hydrogen. Maybe that flow sheet I showed you about what we've developed over hundreds of years needs to be rethought if we go down this hydrogen route. So I'll talk to those first 3 options, all right? And I'll try not to take too much time because I'm already stretching my luck. So I'll keep going. So this is the one that's been commercialized. This was actually done in the West Indies in 2005, 2006, 2007. And they made hundreds of thousands of tons of iron using hydrogen, 100% hydrogen. And they then got that iron and they sold it to steel mills and they made steel. So it's already been done. It's already been shown that it could be done. This is a fluidized bed process, a 2-stage process, quite complicated process. I don't know whether it's the answer to the world, but it did work and it did make commercial and they made money from it. Now, it is telling to say it's no longer in business, so that's probably an important thing to point out, but they did do it commercially for a number of years. One thing to appreciate is that this iron made from this has almost no carbon in it. So it's basically carbonless, an iron, not a steel, it's a kind of an iron with no carbon in it. And when you have carbons with low, ions of low carbon, and you put it into the next process, what tends to happen is you make a lot of FeO. This is to do with the chemistry of the system. You make a lot of FeO in the slag. And that's exactly what happened when they put it into the furnaces. And these people, to get over that problem in the electric furnace, had to inject carbon to reduce the FeO. And they also had to put carbon in to make sure they got good stirring in the bath, because the carbon does more than just take away the oxygen, carbon is used all through the steelmaking process. And so they had to adapt the electric arc furnace steelmaking process for this kind of iron, and it was not untrivial. It was actually fairly challenging. And if we go to a large scale, these problems will get even more so. One thing to appreciate is that we know that if you add more and more DRI into an electric arc furnace, you will push up the energy requirement and the amount of CO2. In fact, if you keep pushing it, you'll eventually get to where the blast furnace is. All right? Now, this line is drawn on the basis of high-grade iron ores. Now, I mentioned to you that our ores are getting leaner and leaner, including in Australia. So what is also happening is that if the world swaps to this route, if it swaps to some version of this route, this line will get steeper because we'll be digging out more and more low-grade ores, and we'll have more and more, and we'll be back to the same problem that we were in the first place. The only way around that is by, first of all, trying to make the ores as rich as possible, but secondly, by making sure that all the electricity, the AF, is renewable. Otherwise, we've got nowhere. So this graph is very interesting, and the slope of that graph will change as ores degrade. And that's something that a lot of people don't realize. People who know a lot of steelmaking realize, and it's a non-trivial problem and likely to keep us occupied. Now, in Europe, they're pursuing these hydrogen options with great glee and great investment. And this is driven by a strong political agenda in Europe towards decarburising their economy. And two of the most prominent ones is there's the plant in Luleå called Hybrid, which is based on the HYL technology. And in Germany, at Thyssenkrupp, they're replacing the hydrogen in the blast furnace. So let's talk a bit about that, because I've got some hot news about that. So the blast furnace has all these tuyeres where you inject your gases, and this is where they're injecting the hydrogen. And what they're finding is that as you inject the hydrogen, you create energy balance problems here, because the reactions between hydrogen and iron oxide are endothermic as compared to exothermic with carbon. Reminding you of high school chemistry. So endothermic sucking in the heat and exothermic pushing out the heat. So these endothermic reactions cause all sorts of issues down below here, in this area here, what they call the raceway in blast furnace parlance. And they've done some tests and some calculations. This is one of the lead engineers sent me this slide. It's very nice of him to share that with you. And he's showing his calculations here about how much hydrogen they can put in. And what they say is that the limit is 27.4, a very precise number from the Germans, I thought, 27.4. And that gets you down on this graph down to about 1,200 kilograms of CO2 for production. So in other words, they're only cutting the production by a bit, and they find that once they try to put more hydrogen in, they actually start making things worse because they have to compensate for these endothermic reactions. And you'll see that the graph is going up as you push more hydrogen in. All right. So it doesn't look like the blast furnace is such a great candidate unless there is some innovation. And in fact, the official strategy of Thyssen, which they just released quite recently, is actually to only put hydrogen in the blast furnace as an intermediate measure. After that, what they want to do is put more and more DRI plants in, and then that's their strategy. So it's only a small intermediate. So it doesn't look like the blast furnace is the answer, simply put. It's too complicated to bring the hydrogen in there. So in ArcelorMittal in Hamburg, they're going the other way. They're going for a Midrex plant, and they're putting 100% hydrogen at demonstration level, and they're using grey hydrogen directly from the natural gas. So what they're obviously doing is trying to see whether they can make it work and hope that somebody else innovates with the hydrogen production to make it cheaper. That's basically what I think their strategy is. All right, what does this mean to Australia? Wow, it has big repercussions to Australia. Well, how will our ores behave? What would this mean to our iron ore industry? And in fact, a CRC was just successful, which I'm part of. Gus Nathan, I think, is at this talk, is heading up. And he convinced the federal government to put $40 million into investigating how to lower the greenhouse gases of heavy industry. And one of the big questions in that CRC, there's a lot of iron ore companies involved, is how will our iron ores perform in a hydrogen-based iron making process? What will that do to our iron ores? How attractive will they be? What will it do? What will we need to do to succeed in that market? And as I've already mentioned to you, the gangue content in our iron ores will be very, very important to this DRI EAF route. So what can we do? Can we get the gangue out? Can we get those silica and aluminas out? What can we do? I have good friends at CSIRO. They might be listening. Keith Vining. That's what keeps him up at night. He's trying to work out how can we get these gangue materials out of the iron ore. And can Australia play a leading role in this? Do we have to just sell the iron ore? But can we do something more? And I want to bring to your attention that Australia has phenomenal resources of solar energy. I think you all know that. And our resources are exactly where our iron ore is. What a wonderful thing, all right? And people like me and John Pye at ANU and some other idealistic professors and people, we say, why don't we just directly use the sun to make concentrated solar energy to make iron ore, right? They make iron, to process iron ores. And it would take me a long time to describe this all to you. But I've done quite a lot of research in understanding not just the science of this, but the techno-economics of using concentrated solar energy to directly make iron. And when you think about it, it cuts out the middleman. It cuts out making the hydrogen to use the, it's saying we can try to use the sun's energy directly. And when we're doing these experiments at Swinburne, we use a solar simulator. That's essentially 7 cinema lamps shining on one spot. And you don't stand there when it's on, I can assure you. That's a very hot place. And there's a DRI that we've made in that furnace using that kind of approach. And you will probably know that Andrew Forrest has recently been coming out and saying rather loudly that we need to start thinking about this as an opportunity, that Australia could be a leader. Because we have good renewable energy resources, because we have iron ore, why don't we make hydrogen and why don't we make steel? And we should become a leader. And I'm inclined to agree with him. So my final thoughts are, and I hope I haven't made this too complex, but my final thoughts are, the simple way to decarburize the steel industry is to increase the use of scrap and combine it with renewable energy. That's the easiest way, the most obvious way to do something. We can make steel using hydrogen. It's been shown to work. It can work. At the moment, green hydrogen is not maybe at the right scale. Hopefully it will come at the right scale and we can lower the cost. There are issues around processing hydrogen generated DRI and electric arc furnaces. They're not trivial. They're quite important. And there needs a lot more thought put into that. That's something that's not been given enough consideration. I just wrote a paper about that. And I've got a lot of reaction to that topic because people are starting to wake up to that. And if the EU goes radically down this hydrogen route in a hurry, what will that mean to the world steel? Will they have to put a tariff war if nobody else follows them? Because at this stage, nobody thinks that it will be cheaper, right? It may be cheaper, maybe 40, 50 years from now, but not in the next 10 years. I hope that's wrong, of course. And can Australia be a leader in this? Can we not only just think about how our ores will sell, but can we think about taking the lead? And who will lead that? Who will invest? Who will make that happen? This is a political question. I'm just a humble professor. I have been raving on about steel for too long now. I should be quiet, and thank you for listening to what I had to say.
Fantastic. So if you could turn off your screen sharing, and then I'll invite people to put questions into the chat function, and I'll pass them on. So here's the first question from Malcolm Jenkins, who incidentally is also the chair of federal ANZAAS. He says that BHP attempted DRI HBI plant at Port Hedland between 96 and 99 using FinMet, whatever that is, but lost their license due to accidents with hydrogen. Oh my goodness. Will the risk profile of using hydrogen at high temperatures represent a major deterrent to uptake of this technology? Yeah.
So one of the so first of all, there other people have built those processes around the world and they have operated safely. The unfortunate sequence of events at Port Hedland means that what Malcolm just asked is asked at every time I present, because there's always somebody who can remember that. And I think, Malcolm, it's important to understand that when there's been a car accident outside your house, it doesn't mean that there's been a car accident outside every house. And I think there are serious issues around safety of hydrogen with DRI, but there are large industrial plants around the world that already operate with large amounts of hydrogen and they don't have any significant issues. Midrex has built a major industry on that basis. So I hear the concern, but we should understand that, you know, there's quite a lot of companies that do this and they do it with apparent safety.
And now a couple of comments. So one is now an hour old, but it's from Francis Saparovic saying that Brisbane has been approved to host the 2032 Olympics, which is not completely on topic, but still it's great news. Lynn Dalton says, great talk, thank you. And Bob Aikenhead also says, great talk. Thinking globally, with China as the biggest steel producer, what interest is there in China in green steel?
Yeah, well, definitely the leaders at the moment are Europe, all right? And what's happening is the Chinese are watching and they will make some investment. But if I spend a lot of time in China, and they are clever people, but they also like to watch other countries take the risks. So I think they're watching quite carefully what is going on in Europe before they would make really serious investments in their own steel industry. Something also to explain in China is their steel industry is closely intertwined with their cities and their community. So, for example, closing down a blast furnace, for example, in a major city in China is a major, major social political issue, more so than it is in Australia. So there are big issues there, but I think they're watching what the Europeans are. They are clever at metallurgy. I'm sure they'll invest when they feel that they can win at it. So I think they're watching is my answer.
I've got a question for you. Who is listening to you? Is it the politicians? Is it the public? Is it industry? Whose ear do you have, and who's paying attention? And who do you need to convince?
At the moment, the federal government and the opposition are quite pro steel industry. They got scared, I think, during the whole mining boom, where we saw a lot of our manufacturing very badly affected. And they see, well, if you don't have a steel industry, are you really a serious technological society? And that's probably, right. That's probably correct. So I think they're both pro steel. The current government is quite pro going down the route of using natural gas as an intermediate to make hydrogen, and they're quite supportive. The iron ore companies are quite supportive of people like me at the moment, and people who are trying to understand this, because they realize it's likely to have a strong impact on their industry and they'd like to understand it. So I'd say there's quite supportive environment. Actually, to be honest, David, I don't remember a time that's better to be a steel researcher in Australia in my life, because everybody is very interested in, very interested in that issue.
So what do you see as the main barriers to going forwards on your plans of step 1 and step 2 and so on?
The step 1, the one about the renewable energy, that is largely an economic political issue. It's not such a technical issue. The other one, the second one, about introducing hydrogen into the DRI and the impacts it has on steelmaking, and even introducing more hydrogen into the blast furnace. Maybe we can be cleverer than the Germans. There are major technical issues. So, for example, at University of Newcastle, they're working with BlueScope, trying to understand more and more hydrogen coming into the blast furnace. People like me are working with steel companies, trying to understand what would happen if you had those sort of ions coming into your steelmaking process and what that would do. So, yeah, the steel companies are interested and investing in various research. So in Australia at the moment, we have the Steel Research Hub at a University of Wollongong. I'm a program director in that, and I'm involved with the HILT CRC, which also has a large program looking at these kind of issues. So the companies are putting money and time into these issues.
A couple of questions from your fan club. Gus Nathan says, nice presentation, Geoff, thanks. Despite its advantages, there are many challenges with using solar thermal for industrial processes, particularly matching the variable input to a steady process and the differences in scale. This is particularly true with the beam down that you showed, where the largest peak input demonstrated to date is about 10 megawatts. Can you please explain how addressed these issues in your techno-economic analysis?
Don't you hate a well-informed critic? I know Gus very well. Yeah, Gus, so basically, just to clarify, solar thermal has been demonstrated as a technology for electricity generation. What holds it back, and I'm just about to publish a paper in the Journal of Cleaner Production, Gus, which goes into detailed techno-economics about solar thermal processing of metals. What holds it back is the capital cost of the mirror system, the heliostat system. So basically at the moment, it's a bit too expensive. Now, it's, to give you some sense of it, to put in a meter squared of mirror system into a heliostat system is like $150 per square meter US. If you could get it down to $100 per square meter, then it would become much more attractive and something that probably companies would invest in. So I think the good answer to Gus is that he raises legitimate points. But if we can innovate with the heliostat system and get the cost down, these things will look more attractive, and I think could happen.
Zushi Lee says, Geoff, wonderful talk, thanks. Slide 18, the difference in CO2 emission between EAF scrap and EAF scrap R, could it be larger than the slide shows?
I think he's right. Sushi's also a very well-informed critic. He's a professor of steelmaking at Warwick University, and he's well-informed. And I agree with him. I didn't generate that particular chart. I think the figure for the scrap could be a bit bigger. I agree with him. So well done, Susie. You spotted a good point.
Yeah. My motto says China has ordered 10 quantum EAFs and is starting to convert. So I guess that's a comment.
Yeah, can I comment about that?
Yes,
yeah, they have done that. I was aware of that. You have to put in perspective, this is a steel industry of 900 million tons. So we're probably talking about, you know, a tiny bit. Yeah, but it's true what he said.
Start. Yeah,
it's true. It's true. It's true what he said. Whoever said that, he's well informed. You've got a very well informed audience here, David.
Bob Aikenhead, who's also on the Victorian committee for ANZAAS and was also the person who suggested you as a speaker. So I've got to give my thanks to him because he's done an excellent job at coming up with fantastic speakers. He says, where are things at with direct hydrogen production from experimental nuclear reactors designed for that purpose?
Yeah, sorry, and this is I have heard a couple of talks on this, but I must admit I don't know as much about that as I'd like. There are people advocating that you should do it. Well, there's people advocating you should do it from organic materials, right? There's a whole lot of people working in that area, and there's a whole lot of people also looking at the possibility of combining it with nuclear power. What I would say, and I'm not saying those can't work, but what I would say is at the moment they're all at a fairly small scale, where the electrolysis technologies are already at quite a decent scale. So that doesn't mean that we shouldn't investigate though, but I didn't have really detailed information on those to present. So I concentrated on the two ones that are closest. But I'm open to that idea. Whether our society is open to the idea of nuclear powered hydrogen generation, I don't know. But at least technically, I think it should be considered.
Yeah, yeah. All right. So I think the rest of the comments are all praise for a great and enjoyable talk. One last question from John Pye saying, "Hi Geoff, thanks for the talk. Wonder if you could comment briefly on the work that's out there on direct electrolytic iron ore reduction. For example, Boston Metals, which the
I know these
invested in."
Yeah. All right. This is John is also an extremely well-informed critic. These are all my collaborators and friends. And so John raises, there are people who advocate for the idea that you should use electrolysis of slags to directly make metal. And their vision is that you have a large solar photovoltaic system feeding into an electrolysis system, and you make steel that way. And actually, one of my PhD students worked for Boston Metals, and he's always telling me what a great idea it is. I think the reason why people don't invest in this very much beyond a small scale is because electrolysis has a reputation for being very high capital. And I think that what people are worried about is that the capital investment to get the amount of steel that you want to make is going to be too large. My PhD student, there's something about Boston. It's MIT and is really crazy about this topic. So this particular student is a graduate of MIT, and he's all the time advocating that it would work. But I think the skepticism comes from that. It's the cost of scaling up the things. But I think it should be considered. At the moment, I'm a little bit skeptical, but it should be considered.